Definition: prostate cancer is a heterogeneous disease, but current treatments are not based on molecular stratification. We hypothesize that metastatic castration-resistant prostate cancer with DNA repair defects would respond to polyadenosine diphosphate (ADP) ribose polymerase (PIRP) inhibition with Olaparib.
Prostate cancer is a heterogeneous disease. Genetic testing is not currently part of the treatment algorithm, but could DNA repair defects influence the response to prostate cancer treatment? The authors of this study hypothesized that metastatic castration-resistant prostate cancer in patients with DNA repair defects would respond well to poly-ADP ribose polymerase, or PARP, inhibition with olaparib. 50 patients with metastatic castration-resistant prostate cancer were enrolled in this phase 2 trial. All 50 had previously received standard therapy with docetaxel, and 49 had received either abiraterone or enzalutamide. In the trial, they were given 400 milligrams of olaparib by mouth twice daily. Tumor biopsy specimens were examined for known DNA repair defects. Of the 49 eligible patients included in the final analysis, 16 had an objectively defined response to olaparib. Of these 16 patients, 14 were found to have a DNA repair defect. Anemia and fatigue were the most common severe adverse events with olaparib. The authors speculate that if their results are replicable, patients with DNA repair defects will have a response rate to olaparib on the order of 80% or better. Full trial results are available at nejm.org.
Applications in medicine: ovarian cancer, prostate cancer.
In your clinical background, I want to get your take on ODAC's recommendation against accelerated approval for a PARC inhibitor and the FDA's final decision.
The drug is known as olaparib. I couldn't possibly disagree more with the determination of the review committee. I don't know that the FDA, is best of my knowledge, has not made we don't hear what the FDA says often. My understanding is they've said, do more research, do more studies. I think the data on this particular drug is overwhelming. As a randomized phase 2 study and a lot of data that supported it, it basically showed that one could almost triple the time to disease progression in a randomized trial in, again, a very specific setting with the use of this agent versus, in this case, it was a placebo control. But I think in addition to that, I have a fundamental disagreement with the approach that medical individuals, as expert as they may be, and of course I would put myself in that category. I've been involved in ovarian cancer research for the last 30 years, I've said, but I would say that these decisions on risks versus benefits in the setting of a truly life-threatening situation should be made by the patients and their families.
Pros and cons. Pros: olaparib has durable anti-tumor activity in men with metastatic, help damaged cells to repair themselves, and olaparib works killing cancer cells. In cons, we have nausea, vomiting, diarrhea, heartburn, headache, decreased appetite, muscle joint, or back pain.
This video focuses on the biochemical mechanism behind PARP inhibitors, an exciting new treatment agent that can be used for targeted cancer therapy. As the primary carrier of genetic information, DNA and the maintenance of its integrity is of the utmost importance to cell survival. Yet in each cell cycle, DNA is damaged thousands of times by mutagenizing agents like UV light, ionizing radiation, replication errors, chemical agents, and cellular metabolism. This introduces flaws, such as single and double-stranded breaks, into the DNA structure, which must be repaired for cell survival. Two vital pathways for DNA repair involve the breast cancer 1 and 2 genes, known as BRCA1, BRCA2, and poly-ADP ribose polymerase, known as PARP. Mutations in BRCA1-2 are well known for their association with increased risk of breast cancer. In the context of DNA repair, BRCA1-2 recognizes and repairs double-stranded breaks via homologous recombination. PARP is a related enzymatic pathway that repairs single-stranded breaks in DNA. To understand how PARP inhibitors work, we must first consider how PARP functions. PARP is a nuclear globular protein that contains 3 functional domains: an N-terminus DNA binding domain containing several zinc finger motifs, a central auto-modification domain, and a C-terminus catalytic domain, CAT, that houses the protein's enzymatic activity and substrate binding sites for nicotinamide adenine dinucleotide, NAD+, which powers the protein. Within this domain, there is a WGR, tryptophan, glycine, and arginine motif, which serves to activate the enzymatic activity of the CAT region. The catalytic domain also contains highly conserved histidine and tyrosine residues, which are necessary for NAD+ binding. A PARP inhibitor will compete with NAD+ at this substrate binding site. Thus, PARP inhibitors function through competitive inhibition. In the absence of an inhibitor, PARP will be recruited to a single-stranded break site, which it identifies with its zinc finger nucleases. Then PARP initiates poly-ADP ribosylation of histones and chromatin remodeling enzymes. The presence of poly-ADP ribose chains, synthesized by PARP, recruits PARP-dependent DNA repair proteins. Finally, PARP and repair complexes dissociate from DNA for recycling, and the single-stranded break is repaired, leading to cell survival. In the presence of a PARP inhibitor, PARP is still recruited to a single-stranded break site. However, PARP can no longer activate PARP-dependent DNA repair proteins because its catalytic activity can no longer be powered by NAD+. Therefore, PARP remains bound to the DNA, stalling the replication fork through DNA replication. This stalling leads to a double-stranded break formation.
Conclusions. The Olaparib is a value partner in the fight against the prostate cancer with metastatic. It gives more time to the people that are in the final part of the diseases to stay within families. If studies of this drug continue, maybe we should be talking of a cure or maybe a better treatment for every cancer.
My lab here in the Gurdon Institute is focused. My lab here in the Gurdon Institute is focusing on how cells respond to and repair DNA damage within the cells of our body. We're interested in this from an academic perspective, but for many years we've also been very interested in the idea could be therapeutic opportunities for new drugs for other diseases. So the developments that we're talking about today relate to a brand new anti-cancer drug called Lynparza, also known as Olaparib. And what this new drug does is work against serious ovarian cancer through a mechanism that has not been exploited before in the clinic. The basis of this new drug is to target DNA repair pathways within human cells. So it turns out that every cell in our body is sustaining DNA damage, and that damage needs to be recognized and it needs to be repaired. Because if the damage isn't repaired, the cells of our body die. The DNA is the genetic blueprint which needs to be kept intact.